Good morning, everybody. So, so we're the ones that have the alarms that work this morning, yes? We have fun? It was good seeing everyone at the Code Challenge last night. Tomorrow night, again, is IoT Hack Night, where registration has been filling up. Again, we have a limited number of Raspberry Pis, which are going to be running the hardware, which will be running the software, which we're all going. So again, please remember to pre-register if you'd like to save your slot for the IoT Hack Night. Something else that's probably worth mentioning, the Summit app and the Lanyon Online website has a section by which you can add a session to your calendar. This is more for your scheduling. It's actually not a pre-registration. And even though I think we've communicated that a little bit, there still seems to be a little bit of miscommunication. So I want to be completely explicit about that. If you're looking to get into a talk and you believe it's going to be a popular one or a difficult one to get into, we want to make sure that you're able to do that, so maybe arrive early and get in line. And we'll look at other ways to resolve that in the future. Today, the DevNation portion will be shutting down before 4 o'clock in time for the Summit launch and middleware keynote. We're going to be joined by the greater Red Hat Summit group as a whole, which is awesome. They'll bring in some fresh blood. It'll be some great, it'll just be bustling in the hallways. And we have the keynote this afternoon, which will be pretty awesome. So as promised yesterday, we have a Pulse session today. We picked that one last night. That will be Emmanuel Bernard of the Hibernate team doing a free-form discussion on Hibernate, on data, how NoSQL has influenced relational database storage and how the two complement each other instead of one replacing one another. It should be a really great session. So that's today's Pulse session. That'll be at 11:40 after the keynote. But this morning, for those of you, the early bird gets the worm. This is truly an exercise in why all the studying physics and science in high school really plays out in real life. Felix Ehm is joining us from Geneva, from CERN. And this talk, to me, is incredibly fascinating. So let's take a look at how open source is being used to power some of the most innovative, exciting, expansive, and important experiments in the world. Felix Ehm, everybody. Thank you. Thank you. Yeah.
Thank you. Yeah. Good morning, everyone. Thanks a lot, Andrew, for the good introduction. My name is Felix Ehm. I'm from CERN, from Geneva. And this session this morning is about how we use open source software for the Accelerator, which is presented here in the first slides. And so far, I've been enjoying this conference really a lot. I've met a lot of really interesting people. First time for me being here, and having talked with people from all different kinds of technology sectors is really exciting for me. So it's also for me a great pleasure being here. So this session this morning is about how we use open source software in the control system. And just to give you a short introduction about myself, I'm a developer, I'm a service manager, developer for a monitoring system and alarm systems, which are being used in our control system, as well as JMS service manager. In my previous activities, I was in the large storage systems and computing grid environment, as a short background. Now, I have to admit that there are a lot of people at CERN. There are about more than 10,000 people, and a lot of them use open source software. Can only speak for our team, for our group. That's why I had to put this here. So there's a lot happening at CERN. That's our stuff. Very classical presentation, a bit on the content. I will start with an introduction to CERN and the Accelerator control system, as well as then afterwards using open source software. So why we're using open source software, what are the reasons, what are the good ones, and then concrete examples how we use it, where we benefit from it, and finally also some couple of words of also how we share knowledge into the community. So to begin with, what is CERN? So CERN is a organization for nuclear research based in Geneva, and it originally stands for Conseil Européen pour la Recherche Nucléaire. That was in 1954 when it was founded, and that's now 60 years ago. So we've got a 60 years anniversary, which is really cool. It's based in Geneva, Switzerland, has about 3,300 staff members, so they're directly paid by CERN. But then in addition to that, we have about 10,000 people coming to CERN, using the facility, joining the research community. And these are people coming from all over the world. So although CERN is being financed by its 21 member states, European member states, people from all over the world come to CERN to join the research activity there. Now, it's a very peaceful environment. It's very stimulating. It's very fascinating to work day by day with different people, going to lunch with different people at different stages. So that's very cool. What's the purpose of that? Well, the purpose is that we build large machines in order to produce particle beams. So you can imagine these are ions or protons. And we accelerate them and let them collide, and then try to trace the fragments to find out what's happening, what's inside. So it's basically, I took this analogy a couple of years ago as well. So it's basically, when I was a kid, I had a nut, and I wanted to know what's inside. Well, what do? Basically, you smash it. You try to look what's inside. And that's what very roughly we're doing here. And on the right side, you see an illustration of two particles colliding in a big detector. So that's the idea, is to find out what keeps the world together inside. Now, we need a lot of infrastructure for that. And here you see an aerial view of CERN, which is on the bottom. You see down here, there's the CERN campus. On the right side, you see the airport and the Geneva Lake. And then you see the big ring, which is the LHC, most prominent machine, which we have, the Large Hadron Collider. Now, that thing is about 27 kilometers long and 100 meters under the Earth. Whereas I think that corresponds to 60 miles and 328 feet, 1.564 inch underground. Well, the second ring, which you see here, is SPS. It's the second largest one. And you already can guess now that CERN does not exist of one accelerator. There are many of them. The ring itself, that's an illustration of and the distribution of the big experiment. So LHC consists of two beam lines, and the particles they go counterclockwise in that ring. So we've got 4 experiments: CMS, LHCb, Atlas, and Alice. Now these are detectors. In all those points, we let the particles collide or go to fixed target, like LHCb. The particles, they go actually nearly at the speed of light, so that's 11,000 times a second. They pass one single point. And then, although CMS and Atlas, they're completely different build, they target at the same scientific goal. So they're trying to confirm each other. And just a word to the tunnel. The tunnel itself consists of this blue and white, actually, magnets. So these are tubes, and in this tube you've got 2 beam lines. And these tubes, they produce a magnetic field in order to keep those particles in the circle. Otherwise, it will just go straight. So we were still accelerating them and keeping in the circle. We started in 2010 with a decent 7 teraelectron volt. We ramped it up in 2012 to 8 at the collision points. And then we had an upgrade phase between 2013 and 2015 where we upgraded the machine, we made it stronger, higher amps to sustain more energy. And now we just successfully restarted in April with a new world record of 13 teraelectron volts, so more energy to even crack more things. That thing, this little beam line, by the way, this is cooled down. So that's 27 kilometers of cooled down metal. This is cooled down by 120 tons of liquid nitrogen, which is basically the annual production of that stuff worldwide. And then this is the primary cooling. We've got a secondary cooling, which actually cools that down. It's 10,000 tons of liquid nitrogen. It's liquid helium. I was wrong. That's liquid helium, 120 tons, and 10,000 tons, which actually cool that stuff, and that's liquid nitrogen. This is the tunnel, and if we go to one of those machines, that's Atlas. It's one of the biggest ones, with about 100 feet long and 82 feet high. It weighs about 7,000 tons. and it has about 100 million channels. So if you see down here that picture, that's a person. It's a really, really big machine, which is down 100 meters in the earth. And as we compare to that, there is so that's one on the bottom, which you see here, and there's CMS. Same people up here, you can see it's a massive, this is the heaviest one in actual fact. So it weighs about 14,000 tons and creates a magnetic field of 4 Tesla, which is about 100,000 times more than the Earth magnetic field. So then we go off to another machine, which is LHCb, and then one of the last ones is Alice. And at the beginning, I'm not sure whether you've seen it, but I wrote at the entrance of the slide, the hottest and coolest place on Earth. Well, literally we are, because the magnets, the blue lines, are cooled down to 1.9 Kelvin, which is colder than outer space. That's a cold part, but the hot part takes place here, where they actually have, during the run, created temperatures of about 4 million Kelvin, of 5.5 trillion Kelvin, which is about 38% more than the previous record was with at the relativistic heavy ion collider at Brookhaven. So these are big machines, and what they basically are big cameras. So you can imagine that whenever something collides, they try to take as many pictures as you can. And this happens every 25 nanoseconds. A lot of data coming out, and how this data is being processed is, unfortunately, I cannot report about today, otherwise it would clearly extend the scope. But if you're interested in building your own atlas, you can go to this website and download all the parts, and you can build one out of Lego if you're happy. So this is also side activities of my colleagues. Quite interesting project. They also have other ones, all the accelerators you can rebuild. These, by the way, these are 9,000 parts. I find it quite impressive. Somebody sits down and assembles a SOAR. Well, to continue, I said that LHC is not the only accelerator. We have more of them. We have a full chain of accelerators. And all of these accelerators, which you see here on the slide, they basically need to be controlled. There's a lot of equipment being involved, and there's a lot of services being involved. It starts with software services, computers need to be monitored, there's electricity, like power converters, there's safety and protection systems. We have a very high energy beam here. That thing has a lot of energy, which is also dangerous because it has about the energy of a train going at 150 kilometers per hour. So this is the energy which it has, so it needs to be very careful and protected. The whole machine should be protected. Now all this corresponds to about 85,000 devices. So a device would be, for example, temperature sensor or a door being open-closed. And then corresponding to about 2 million I/O endpoints. So that needs to be all controlled somehow. And in actual fact, it's much more when you include all the subsystems. So that's a vast amount of data which you need to somehow swallow, process, analyze, etc. Everything happens from one central point. This is the CERN Control Center. Now you can imagine that this is something like the NASA Space Control Center, where people sit 24/7 and watch the systems. They control, they coordinate phases of injection, ramp up, and when they're ready for physics. And this is on the left side, the 4 aisles targeting at different areas of the facility. And on the right side, that's a typical view of an operator, which they have in front of them. A lot of screens. Up here you have what we call so-called dashboards. They show static information all the time. Then we have those consoles down here. I think we have around about 400 screens or something like this meantime. And what you already can see here is a lot of GUI applications which the operators use. And I can tell you already out of today, none of them are proprietary. They're all Java-based GUIs, which have been developed either in-house or in collaboration with other institutes. Now this is already you can already glimpse where that open source plays a major role in our environment. Now, if we look at the control system from an architecture point of view, we have on the bottom layer, we have the devices, so what I was mentioning before, temperature sensors, etc. And then we have embedded computers which allow accessing them. That means that you cannot only monitor, but you can also control them. You can do sets. Then in the business layer, you have general purpose application servers, but also specific ones like machine protection or alarm systems. Then you have, on the top layer, you have graphical the graphical layer, which is being used by the operators themselves. And all of this is being interconnected with communication middleware. And I will come to this later on because this is actually being driven by open source. Now, if you come to the software, a couple of numbers here which we have is there are about 400 graphical displays started, if not more, 300 application servers, around 3,500 embedded processors, which are running on those embedded computers. And all the software is developed by more than 80 people, and I think more or less 10 million lines of code, which is a lot. So a lot of software is involved. And what you actually see on the top part is only the peak of the iceberg, because you have much more complexity underneath. And if we just, from the control system point of view, just have a look on a graph which is shown here. This is shows the connection from middleware point of view between the processes. So each dot is a process, and the lines are the connections between them. We have around 90% Java and 10% C++ in this picture, but some of those connections may also be established only temporarily. This is just a snapshot at a certain time. A lot of software is involved. I said this before, and a lot of software is used with open source. And this is the content which is broken, but it supposed to tell you that we have 4 chapters where I introduce you to CERN, and which we had before, and then how we use open source, what are the selection criteria of using open source in such a critical environment, and how do we maintain this software at some stage. I tried to come up with a map of products which we're using, and I'm sure that I forgot a lot of them. I think not many more could have been fitted on this picture, and I tried to, with the size of the icon, to emphasize the importance and the usage of these products. And just as a very, very short, I would like only to highlight a couple of them because I'm going to go into detail later on. So for example, CentOS is one of our platforms which you'll be using for development and production. It's a CentOS system. Then we use a lot of OpenStack for our virtualization. And I know that my colleagues from my IT department, they run about, I think, 12,000 nodes with OpenStack as of today. But there's also other things for development, which is very important. So we use a lot of Spring. Java is, as I said before, one of our main programming languages. And then we have build tools. We have an own in-house build system based on Ant, but then we're now moving towards Gradle. Eclipse is definitely one of our first development tools. And then Apache, JavaVex, a lot of things come into the game when development comes in. Now, this was for Java, but we also use the very same for C++. So we're profiting a lot from all the GNU tools, GNU build tools like glibc and GCC as a basic tool to compile code, but then also external or other ones like Boost libraries, which is a framework which provides a lot of existing functionality, like Spring for Java. Now, why do we choose open source? Well, one of the main key points is that we can read the code. And this is very essential. We are engineers. We like to know what's happening inside. We're already fighting with so many other levels in our own code that anything which is a black box is an obstacle. Understanding what's happening inside also means that there's a good chance that we can extend or read the code and fix the code which is broken. And that happens already a couple of times. So for example, reading the code, we started in the early days over 10 years ago with proprietary J2E or EGB containers. And one of the stories where one of my colleagues really got upset about, he had a bug in the application server and he tried to fix it, and he was decompiling the code basically and then tried to find the problem. This is not very maintenance friendly. And debugging there is a pain if you don't know what you're dealing with. Now, when it comes to flexibility, we believe that open source gives us more flexibility in terms of that we're not bound to a single entity or manufacturer or producer. We have, if it is open source, we can take the code, we can partly also build it ourselves. Our systems run for more than 20 years. If you ask today a young guy about how long his software will survive, I don't know, what's the time? I mean, 5 years is already pretty estimated as a long time. If you consider 15 and 20 years for a software, then you run into completely different problems. Like, for example, we have vendors, proprietary drivers, and they at some stage said, well, you know what, we don't have enough turnaround, so you know what, we just dropped the support for this, and by the way, here's the code. So we were left with that code. So they gave us actually the code, and that's the point where we also then had to build it ourselves, and when we discovered that actually the code was, you know, very happy that it was running so long because it was really ugly code. Well, then this, one of the main reasons is also that we believe that peer review produces better code. And as such, with the good code in place, well, the quality of your system goes up. And finally, of all reasons, is that it very much fits our policies of sharing knowledge and exchanging or knowledge dissemination. Now, when it comes to the selection criteria, well, we know now why we use open source, so let's try to find a product for a specific problem. Then we look at certain things like, for example, the user community. How active is the product being maintained? How many releases have been made? And, for example, how many open bugs are there? When was the last one fixed? But also, changes are backward compatible. I can tell you, we have an environment where if you try to put in a new library version which is not backward compatible, this is really, really pain. The integration phase, for moving one version to the next one, if it is not backward compatible, is just a nightmare and costs a lot of time. So this is, we're looking very much onto this. And one good example here is Spring, because we've been using Spring from the very early moments, I think from 1.0 onwards. And one of the main guys behind, Jürgen Höller, behind Spring, he even joined us in the very early days and, for example, proposed doing presentations together and papers on this. So Spring, we managed to go from 1.0 to 4 today without major impacts. And that's a good example for backward compatibility, at least from our perspective, what we have experienced so far. Product involvement. I mean, where does it go? What are the plans for it? What is the perspective of that product? Is it going to be joined with other products, et cetera, et cetera? But also, we love toolkits rather than full-fledged frameworks, which basically, if you imagine from a programmer's point of view, they call us. That's what we don't like. We like to call them. So we can use those toolkits to adapt it to our specific environment. That's where we see the power of modular components. Then we have dependency hell. Who loves the dependency hell? I mean, seriously, that's okay for direct dependencies, but if you go for transient dependencies or dependency of dependencies, we heard a talk about this yesterday, how much pain and headache it costs. I just said before, 1,000 jars in production out there. You can imagine what pain we're facing here if they're uncontrolled or a new dependency just quickly coming in or not. So we love products which have not a lot of dependencies, sleek, modular, and thin. Diagnostics. With such a large stack of software in place, diagnostics is a very important point. JMX attributes for Java. Exposing those information helps us to look what's happening inside the process without stopping it. And then, of course, enough logging. That's something which I today think is so important that everything is just being taken for granted. Can we get some commercial support? That is very interesting for us because we can get the support from a company. So that does mean that we also pay for good open source software. But we do also have some very good relationships with the companies. So they, for example, they give, they use us as a testing facility. They say, this happens on the hardware, but also software side. They say, okay, here, you've got an environment which is not data by day, so just give us back your feed, just feed us back your experience with it, and then that's a win-win situation for both sides. Does it implement standards? And by standards, I mean established standards, but also de facto standards. Like I believe that JSON is kind of a de facto standard, because standard means that we can actually, once we have chosen a solution, we can get onto another one without any large headache, without integration efforts. And of course, when it comes to C and C++, 32 and 64 compatibility is something which is now still with systems, which I told you 20 years, which are running 32, moving them to 64 is something which is not negligible. Coming to the next third topic is about how we use open source really in our environment for the accelerator controls. And I would like to start with an area which I'm familiar with, because I'm basically running that service, is ActiveMQ for large-scale messaging. And just to give you an idea about how we use ActiveMQ, this is a picture from the beginning. And I told you that presentation and business layer are both mostly Java services. So this is where ActiveMQ comes in to cover the need for a scalable and reliable data transport of data. We started pretty early, already in 2005, so 10-year anniversary, we have ActiveMQ in production, and it was chosen as let's try it out, let's see, there's a movement, let's give it a try. ActiveMQ was very new those days, so it was added to our middleware API. So the applications actually don't use ActiveMQ directly, but they just use an API. And then that was all good. We had 2 interconnected brokers that was forwarding the data. That was easy. Little data, little projects, was very easy to use, did the job. But of course, once things are working very well, people like it, they hop onto it, and then at some stage, more users came in, more data was sent around, higher quality of service was requested, for example, high availability, so 0 downtime, rolling updates, etc. But also queues, persistent messaging, etc., etc. Support for non-Java clients, Stomp came up in the recent years, and also serving data, so separating, playing within the topology of the brokers to serve also other networks of data without interaction in the other way around. Then, what we had to do was we had to adapt the infrastructure, and we were able to do that. Now, this was a cool part. That made fun. So from 2005, when we started with 2 brokers, we were basically scaled up until 2013 to 29 brokers. This is the same number as of today, because I told you about the upgrade phase, so ActiveMQ infrastructure as before, and we have 29 brokers in production as of today. So how are they deployed? They're not deployed as a large, massive cluster and everything is interconnected, but we have single entities for specific projects, but also a couple of high availability clusters. Now these are 2 brokers deployed on 2 machines, and the endpoint is known by the client, so he can ping pong between those 2 guys. This has the advantage that you actually have not a massive, huge cluster where every message can go every path around, but you have a manageable entities which you can monitor and check. And as of today, ActiveMQ is a vital part of Beam instrumentation. That means if that service does not transport any data, or if it has any hiccups, it means that there is no particle physics as of today. And that, if you consider that LHC is about $100,000 per hour to run or not run, you don't want to be that person being on the blame list on Monday morning when it is about what happened on the weekend or the week before. So some numbers, just to give you an idea about the service itself, how it's being used, is, well, we have about 300 applications, a lot of connections, many topics, but most of all, at the bottom you see a lot of messages going in, but also message going out. And this does not correspond. You see that we're producing much more data than we actually consume. All in all, I must admit that for numbers of 2013, we achieved a pretty good uptime, and that is, from my perspective, a success. This is where open source as a full solution helped us to run a very, very stable service. Now, during 2010, when everybody started up, I got the information before with the SLAs was saying, hey, we're sending about 1 terabyte per day of data. Well, fine, good, fair enough. That's okay, I can do that. Then press was there, everybody's looking at CERN, you know, first beam in 2010, and then in the background, actually, what happened was that there was 150% of data, increase of data being sent around, so 2.5 terabytes per day. And this is not a file server or whatever, this is just, it's a messaging system, right? And that was very impressive. That was a very good performance this piece of software showed in 2010. Now, when it comes, this was a full solution, but we also use frameworks and solutions, packages, components within our in-house developed software. And I would like to give an example of how open source modules are being used in our software. As an example, I will take here a monitoring system. So this is a C2Mon project, and it's a project which we have developed in order to create a very scalable and flexible control monitoring platform. So most of the time what we're doing, we're monitoring equipment. And it allows you to acquire from different sources data via those DACs here, and then the server has a business logic, and on top you can have client applications. Now this is not a full-fledged solution, it's not a full solution as such which doctrates what you use. It's actually so flexible. It's an API, and that's an API, so you can add any client application on top of that. But the server actually serves then the data. And it does this, it allows historical data and replaying, so you can say, hey, what happened between 12 o'clock and 2 o'clock? Please replay me this situation, and he will just pick the data from the long-term storage and throw it at your client application. I said it is extendable and modular on all sides, so you can also add modules on your business layer. So we created this, again, it's a toolbox, which we like. So this is what we use in our environment, and we have deployed it for 2 services in our environment. And if we look at using open source and layers, I just draw the picture a bit differently. You already see here that for the communication, reliable communication, we use ActiveMQ. And when it comes to the solutions, we have, for example, EHCache, we have Spring Container, Java Well, MyBatis for the database storage. But then on top of that, we have web application being implemented. We use Bootstrap, and on the other side, a alarm console, which is JavaFX. Now that comes with C2Mon as of today, but any other application you can add as you want. This is just an example for different modules which we use. And how does it work in action? So how do we use it in our production environment? So we have a data acquisition. These are little standalone single programs. And then we have, for example, one which checks JMX endpoints, another one used as an MP, and you can imagine a full set. In actual fact, we have something like 15 different equipment types which we have here. So those guys is sending through a cluster of networked ActiveMQ brokers to communicate with the server on top of that. Now we have also redundant servers, and so we can scale on this level as well. They actually intercommunicate using another open source product, which is a distributed cache Terracotta. This again is being backed up by a hot standby. That means that we have redundancy on nearly all levels. That means if a server is not working anymore, we still have another path. Same for the ActiveMQ brokers, and same for the distributed cache. This distributed cache also allows us to upgrade a server without bringing the service down, the overall service. When it comes to the client applications, we have a couple of them on top, which again communicates via the cluster. So we have web console showing some statics. So we have dashboards, we have alarm console, and even access is being controlled via the system. So with video signals being shown to the operator, somebody wants to enter somewhere the accelerator and says, hey, please let me in. And then the operator gets a video signal. And as soon as the operator says, yes, you can go, there's a full command being sent down to the chain and down to a DAC, which it not only acquires, but also can do actions. And he's then basically triggering the permit. Just number of specs here. Today we have around 91,000 metrics in this system. We have 300,000 alarms and 48,000 business rules. That's what the system does pretty fine. 28 million updates per day. That's just to give you an idea about the amount of data which goes through that stuff. Now, this is clearly, I have to say, that open source here helped us to create a system which is scalable and flexible for our needs. And to say it with Andrew, I think he's using this very often, it's like successfully dot. You can find information on this project on cern.ch/c2mon. We're about to open source it because we see that it's also useful for other people and other institutes. Now, coming to another topic is where we actually combine different open source solutions which act as single services and then make something really powerful out of it. Is when we had, a couple of years ago, we had this problem that our diskless embedded computers, there was software running on it, right? If you try to diagnose those, you don't have any way. They were sending logs through a very old single-threaded log server, and it was really badly written and couldn't scale. And then we said, okay, we need something new. And the idea was basically to push the diagnostic information as close as possible to the expert. And for that, we used open source software like Apache Camel, Mina, and ActiveMQ again as a message bus. So the idea was that we're basically slurping in from any kind of source log information, log4j, or our own log format, and then unifying it in a central place, and then giving it to the experts. Now they find it really, this was very, very beneficial for them because the first time they could just start a GUI and see what's happening on site on the very, very low level software. It's something which they have increased their productivity a lot. And here the key point is that Camel allowed us to remove all this boilerplate code. So you could say route from endpoint that to endpoint that, and you can just implement the message converter, et cetera, et cetera. That was very powerful. That was very flexible for us. And if we look at the results so far, that was pretty good. You know, people liked it. They say, wow, that's good, cool stuff we're doing here. We can look in files. They didn't have this before. Wow. Everything which is very taken for granted in the Java world or in other worlds was kind of new here. But of course, there are new demands. So we want to have more flexible storage. Some data need to be stored differently at other ones. And you know, people, once they have the little finger, they take your whole hand and they want to have more. Because they also find this system as extremely useful. Now again, we're talking here about a huge user community of 100 people or so. And then what we did basically, this is behind me the picture again of the very same system I showed you before with the C++ sources and the log server, and on top the diagnostic tools which receives those live events. And usually we have 800 logs per second, and it goes up to 5,000 logs per second, which is, I don't really know if this is a lot or not. I don't know what if somebody's out there running a similar setup, I'd really like to talk with you about this topic. But what we did was we extended the information being sent, because it's not only important to diagnose a process, because in such a large environment, you want to know what's happening in every corner, so installations, deployments, et cetera, et cetera. And then we threw all this into a preprocessor, which again threw it into Elasticsearch as a database, and from there onwards, we were using Kibana. Now that was very powerful because the user had all of a sudden a web interface, and they can check it. And that's the cool stuff, but at the same time, the open source community discovered this domain, and these technologies came up. And today, you have a very, very good stack of software tools out there. I know that there's also Graylog out there. So this topic is very well explored as of today. We produce, still with this system, around about 40 million logs per day. And this preprocessor in front, he actually has a pattern to recognize duplication of messages. So what he does, he receives a message, he marks it as, well, I've seen it already, puts a marker on it, and puts it into Elasticsearch. And then on one day, we have a lot of data going in, but then on the end of the day, we basically throw everything away, which is being duplicated. So after one day, you see in the curve a reduction of the data. Now, having all this auditing information with the diagnostic and logs, we said, okay, let's put everything together. So we also have the syslog stuff coming from the Linux machines and old legacy programs. Now, this is a very cool system as of today. And the reduction of the messages of 90% by removing duplicates is something which is you don't want to store everything, right? You don't need a duplicated message. Now, this is a very powerful combination, considering that you can collect data from different sources, storage policies in place, and easy access. So this is definitely a very good success for our user community, where open source helped us to reduce the development time. Now, coming to the last part of my presentation today is the sharing of knowledge. This is a topic which is actually embedded in the fundamentals of CERN, in the basic principles. Because when this institute has been built in the very early days, that's a picture of this when they were digging the first holes for the buildings. This whole institute has been created with a spirit to share knowledge, to disseminate knowledge, and for the mankind. This has been stated in the manifesto. So the results of CERN's experimental and theoretical work shall be published or otherwise made generally available. That's a part of our culture. Share knowledge, disseminate knowledge, and on the right side, but basically all the European heads signed this. Now, one of the most prominent examples is Tim Berners-Lee when he published the World Wide Web proposal, vague but exciting. And this is, I think, this is a picture of the original proposal here. Now, that's something which happened already in the early days of '93 when he placed it in public domain. And if anybody would like to see how such a license looked like in those days, now that's what's being written in order to state the license for the software, which was the HTTPD and the library. So, and there's basically here the photograph of the policy going with that product. Now, but there are many ways how CERN gives back to the community. And one of the first things they do is, what we do is, of course, we also pay licenses to open source or to companies behind open source. This is also another way is that we do code contribution. And here I've got an example for this design tool called KeyCat. This is just one example out of many. But here we have, this tool is being used by our team as well. And this is open source software. This is a CAT tool for designing hardware layouts. Funny, we're also open sourcing our own products, because if we see that it is useful for other people, then why not sharing it? And one example for sharing such open source product, I was telling you about C2MON before, but another one, if we had 2 years or 2 years ago, we published it. It's targets at a specific problem. So who of you ever had to debug a C and C++ program? That's a couple. So how many people like to debug C++ programs? That's an honest answer. Very good, very good, very good. So basically, you have limited amount of information there. You can do core dumps, you have log statements if you have them. You can attach a GDB. If you think about real-time processes, if something happens there, and you attach a GDB, you basically stop the process. And that is something which you would like to avoid. Now, we know Java. We know that there are ways to expose information and to read information. That's JMX. So the whole idea is like, well, why can't we have the very same thing as JMX? So that a C++ developer has an easy API to register a metric, to expose it, and to update it during runtime as much as you do with JMX. You can profit from that, and from external, you can access the very same program. Well, everybody who used SNMP as a protocol? Oh yeah. Okay. We found out it's quite complicated. You need to maintain this MIB file. You need to be in the tree of the numbers, and it's quite hard and complicated. We found compared to the concepts which you have, for example, in the Java world. There was no other in those words. And by the way, this SNP is not real-time compliant, unfortunately. And that's why it fall out of our choosing the solution. So what we came up with, a very small, lightweight library, which allows exactly what JMX does for CMX. What it doesn't allow is to set values yet on the bottom. But the idea is that the C and C++ developers have a unified API, and they can register and update metrics during runtime. Now this is a new thing for those guys, because all of a sudden they were able to start either a Java program, or you could also have a little daemon which exposes the very same information via JSON. And they could expect this queue sizes internally, number of threads, et cetera, et cetera. So that was very, very powerful. And all this happens with shared memory technology. So you have, this is being used in order to guarantee low latency, non-blocking calls. And if you want to know more about it, just check out here on CERN.ch/CMX. Very little dependencies. If you want to play with it, go ahead. We find it as, it's currently deployed now, development for 2,000 processes. So we are using it day by day. And as such, we haven't found any bugs so far, but this doesn't mean that there isn't none. There isn't one. But it goes a bit lower than that, than C++ or even further. Going to the hardware level, we have a lot of hardware modules which we buy from vendors, proprietary modules. And if you look at the number of different kinds you have, combined with the time you need to maintain your infrastructure, you inevitably come to the point that, again, like software, you need to maintain it. In terms of drivers, you need to port the drivers from platform to platform, et cetera, et cetera. But like software, hardware also can have bugs. It may produce a different output under different conditions. And if it is closed source, it's very difficult to know what's happening inside. So the main idea is that all this, because it has costed a lot of time in terms of checking what's happening and also paying the licenses, et cetera, we thought about, well, why can't we have something similar like software, open source software, where we all profit from the fact that we can share, we can have improved code by peer review, we can reuse design, we can take something somebody has created, we can change it and put it back into the community. Now this, again, comes what I said at the beginning, it improves the quality of the product itself. Now compared to the software, we have in the end somebody who actually can produce it. And they have, the idea is here that you design the hardware, you create the drivers, which are open source, and the idea is that you have not really a vendor lock-in as such, because it is open. You can check what's happening inside. And you can eventually switch the vendor here. Now this has been, there are a couple of advantages for definitely on the consumer side, I was saying before. So there's the quality is improved, and there is the standardization. If people reuse things, the standards are being established somehow, and the competition on the market by several vendors of the very same hardware means that you can choose between the different vendors giving you better support or lower prices. And this is a big role for us when it comes for the amount of the hardware we're playing with. Then for as a company, well, we know that for open source software, there are successful companies behind open source software. One is sponsoring or doing this conference here. We know the Red Hat, Ubuntu, et cetera, they're doing good with this model. So why can't open hardware be the very same way that we can profit? And for the advantages for companies, it's clear. They can discover open hardware as a product. They know that if somebody designs something, he designed it for a certain purpose. So there's most probably there's a market for the final product. And finally, the initial investment is quite low. If you consider that we design also, at CERN we also design our own hardware. If we now design the hardware, we'll write the driver software, and then we only need somebody who's producing it, then the initial investment for the company is pretty low. This was this effort in this area has increased in the last years, and one example here is the open hardware product. It's called the White Rabbit product. And to explain you a little bit the background of it, it's on the left side you see a picture of the accelerator infrastructure with different kinds of cards or devices, and actually, in fact, deployed at different places. Now, I told you 16 miles circumference of the tunnel means that you have a large distance between the equipments. If you want to having them act all the same way, you need to have a way to synchronize them. And here's the challenge, because you've got latency, different endpoints have different latencies, et cetera, et cetera. And our current timing system requires a lot of manual intervention. So people actually need to go around the place and need to resynchronize with an atomic clock the local equipment, which is very, well, error-prone, maybe not, but it's definitely a big maintenance effort. And the challenge here is to have then finally a central signal so that all the equipment's acting the same way. One example here is, for example, if you want to ramp up the magnets, you want to have this happening all the same way, or at the same time. And this is where White Rabbit project was created to exactly solve this problem. Sorry. So the idea is, we create the design, we write the software, and then we put it into a repository, and hardware vendors can check it. They can find out, is it something which we're interested in? And yes, they were. They found it extremely useful. They found that there is a market because it's a general problem. Latency or synchronization is not a CERN-specific problem. This can be applied in any other places. And I will give you an example afterwards. So what we have today, you can go and buy off-the-shelf hardware which is completely open. The design is hardware, the firmware is hardware, the tools to access it is completely open. It has been established actually as an IEEE standard, and the trick is that this switch, which you can buy as of today from several vendors, is based on standard Ethernet. So it uses, you don't need to have a separate cable to transport that timing signal. It uses established Ethernet standards to do so. If you want to find out more, it's OHWI.org projects. There are more of them on this webpage. And one of them is similar idea, which also being promoted here with the batches. You're running around with, and Raspberry Pi picks up your signal. And there's one project in this open hardware repository which is called Cosmic Pi. And the idea is that you have a Raspberry Pi and you can buy a little sensor and you can assemble your own cosmic ray detector. And this is also in the very same repository, quite interesting. If you're into it, definitely have a look at that. Very cool stuff. Now, I said that this product is now on the market. You can buy it from several vendors, and other people have found use in it. So there's CERN, for sure, which we came up with to synchronize our systems. But GSI, which is a similar accelerator in Germany, they're using, as of today, they're using the very same synchronization method in their environment. But there are also other projects all over the world which discovered the usage and the profit for it. So the reusage of this thing, once you've created it and other people can profit from it, is the idea of this open hardware. Other projects, I said C2Mon, the monitoring system, is open source soon. Indico is a software which was also developed at CERN and it's all about conference management systems. So at CERN, we have a large infrastructure with a lot of rooms, and if somebody creates a conference or a meeting or whatever, we have one tool which allows us to choose which room is free, what do you need, Beamer or not, whatsoever. And this is a tool which we use day by day, and I must admit, it's quite good, actually. It's very good. And you can find more information here on GitHub. Invenio was a library system. These are just examples for software which we think is valuable to the community out there, and you can profit from it. You will find more on knowledgetransfer.web.ch. Check it out if you find something useful. I'm also very happy to answer your questions later on, where you can, if you have specific ones on these products. So to come to the end of this presentation with a question, what would we do without open source software? Well, I can definitely say we will have a very, very, very hard time. And I took the picture from the beginning and put in the logos I had at the beginning, and I tried to figure out, okay, what happens if we take it away? Well, basically, it looks like a Swiss cheese. You have holes all over the place. And although I like cheese, but this is something which is essential. Open source is in all our layers. We depend on it. We like the concepts, and we definitely we use it a lot, and trying to feed back into the community as much as we can. And if one of you guys ever have contributed to one of those or to other open source projects, then I definitely can say that you have participated directly or indirectly to the success of the LHC and all its experiments. And on these words, I would like to thank you very much. And if there are any questions out there, I'm very happy to answer them later on. Thanks a lot.
Hey y'all, so we're tracking about 10 o'clock. Maybe time for a couple questions. If you guys want to stay and hang around, we can do a couple. We'll hand around mics, and then we'll have to book it downstairs and go do some sessions to make sure that we get those before lunch. So if anyone wants to hang around and do some questions, we have some time for that. Else, class dismissed, and we'll see you downstairs for sessions, yeah? Thanks very much.